Okay, probably I will write cyclotron motion. Cyclotron motion. Right. Okay, so let's start first with this situation. What if you have, for example, a magnetic field pointing this way? Oops. So B. Right. And what if I take, for example, an electron or proton and send it along the magnetic field line? So let's say charge Q, and it flies this way, V. And of course, okay, let me write down, of course, the force which we have to use, Q, V cross B, universal, fundamental formula which allows us to calculate force, which a charge experiences if it's exposed to a magnetic field. Right? Let me frame it. Right. And so in this case, what will be the value of the force? Since V is parallel to B, the angle between them is 0, sine of 0 degrees 0, cross product is 0. In this case, magnetic force is 0. In this case, particle is not going to experience the force. It means that it will fly straight with the same velocity forever and ever. Right. So in this case, F equals 0, magnetic force, right? And as a result, we have uniform translational motion. Uniform translational motion along the same line with the same speed forever and ever, right? So as a result, we have uniform translational motion. So it's a boring case, nothing interesting over here. So, but we need to mention it. So now let's move to the next situation. I just separated this first case. Now let's send a particle perpendicular to the magnetic field. Right? So now let's say magnetic field is into the board. Yeah, maybe I will add additional line of, so these are magnetic field lines showing our magnetic field. And now let's assume that we have some particle, charged particle Q, which flies with velocity V. And now we want to discuss this motion, right? So first of all, in order to understand what happens with this particle, of course, we need to realize what happens to the force, right, acting on this particle. Of course, if no force acted on the particle, this particle would fly straight, like in this case. But in this case, force is not 0. Q, V, B, right? So now V and B are not parallel to each other, they're perpendicular. The angle between V and B is 90. Okay, guys, somebody's mic is on. Whose mic is on? Let me mute. Okay, sorry, I have to mute. Right, okay, so in this case, force is not 0. What's the direction of the force? V cross B, V that way, B is into the board, so I have to curl my fingers like this, right? So you see, V cross B, as a result, magnetic force acts this way. We assume the charge is positive, for example, for simplicity. Let's assume charge is positive. So in this case, force acts this way. So that's direction of the force. It's perpendicular to the direction of motion, perpendicular to the velocity. It means what? Which trajectory we're going to get if force is perpendicular to the velocity. This force cannot change the magnitude of that velocity. So speed is going to be the same. It means we're going to have, again here, uniform motion, but not translational. No way. So in that case, what does this force do if it doesn't change speed of the particle? it changes direction of that velocity. So first particle tries to fly this way, then this way, this way, this way, this way, this, and eventually it gives us circular orbit. When the force acts perpendicular to the direction of motion all the time, you see, force is perpendicular to the v, because you remember cross product. The direction of the cross product perpendicular to both of these vectors, v and b. So force all the time perpendicular to v. It all the time keeps, force all the time keeps changing direction of the velocity. As a result, we're going to get circular orbit. Let me draw it. I've been using a plate, right? It's kind of dirty with markers, right? I have to use something. What is available? Right. So let me draw a nice circle. I hope nice. Okay, it should be good. Okay, decent, right? So that's the trajectory, and this is the center, right? And as I said, all the time, force is perpendicular. If, for example, let's imagine that the particle is here, so this is direction of the velocity, but direction of the force still perpendicular, right? So it will be this way, so still force. If particle is here, again, force will be perpendicular, F, right? And velocity is this way. So this is the cyclotron motion. This circular orbit called cyclotron motion, right? So let me check if I mention. Yeah, okay, so now next, let's describe this trajectory. So what does it mean describing a trajectory, this trajectory? It's a circle. If you know the radius of this circle, you know everything about this trajectory. So let's find the circle, the radius of this cyclotron motion. Cyclotron radius. Let's find cyclotron radius. Right? Okay, in order to do that, let me separate this part deeper. Okay. And in order to describe circular motion, you remember in Physics 1, which coordinate system did you use in a previous semester or maybe earlier when you remember when you analyzed motion of satellites, for example, or some object attached to the rope and you spin that rope, that object. Every time you use two coordinate axis along tangential direction and radial direction. Let's do the same here. So let me choose coordinates. This is R towards the center, right? And T tangential. How should I draw it? So that is tangential direction, T. So instead of X and Y in Physics 1, we decided to use R and T. They're still mutually perpendicular to each other. So we can use all those beautiful features of rectangular coordinate system. But now it's more convenient to align them like this. R towards the center and T tangential, right? Okay, and now in order to describe any motion, what can be used? Universal law, Newton's second law. Let's apply Newton's second law for both of these directions, for R and T, like we've done many times again in Physics 1. But you know what, before I start applying Newton's second law, let me write explicitly force. And also tell what's, okay, just basically write direction and magnitude of the force. Right? So before we start applying Newton's second law. Right. So force is over there. So direction of F radial. So in plus R direction. And magnitude of F, of course it will be V and B perpendicular to each other, because that's the situation we decided to analyze. B is into the board, V you see this way. So every time they are perpendicular to each other. So as a result, magnetic force will be QVB, because the angle between them is 90 degrees. Okay, let me emphasize on that. Theta is 90 degrees. Okay, so now we know all the information about the force, and now let's apply Newton's second law. Let's start with the t direction. All right, so now let's apply Newton's second law in t and r directions. So let's start with T1. So force, what's the force in the, what's the value of the force in T direction? T direction that way, force is perpendicular. So force is 0, right? Because there is no force acting in tangential direction. We have only one force, magnetic, and that has a radial direction, right? So force equals 0. As a result, Newton's second law, m times tangential acceleration equals to 0, because the force equals 0. So tangential acceleration is 0. It means that speed of the particle is the same. Uniform motion, like what we discussed conceptually a few minutes ago. Sorry. All right, so speed is constant. So we have uniform motion. We discussed that conceptually, and now we're sort of getting it from the Newton's second law. So now let's do the same for the r direction. All right, so now force in the radial direction equals to mass times acceleration in the radial direction. Which acceleration do we have here? A sub r. Again, it's physics 1. When you analyze the motion of satellites around the Earth, you remember that acceleration which we use? It's called centripetal acceleration, right? Usually students remember name, but most of the time they don't remember the expression for the centripetal acceleration. It's a square of the velocity divided by the radius. Right. So this, okay, let me use something else. So this is v squared over r. Centripetal acceleration. And of course force in the radial direction, it's our magnetic force, QVB. So this is QVB. Okay, so now let's write that down. So it will be QV times B equals mv squared over r. Just application of Newton's second law, nothing else. Again, one velocity can be cancelled. V and this V can be cancelled. And as a result, we can solve it for r. And since it will be radius of our cyclotron motion, let's add subscript cyclotron as CYC cyclotron. So it will be mv divided by qb. mv divided by q times the value of the magnetic field. So that's the cyclotron radius. So let me write it down. So it's a cyclotron radius. A few times I give a problem about this on the exam, final exam, of course, right? And on the formula sheet, I never give this formula. Every time I expect that students are capable just using Newton's second law in the radial direction, in this case force, magnetic force, in this case mass times centripetal acceleration, and I expect that students should be able to do this one line derivation to get the expression for the cyclotron radius. But of course now you have everything available to you during the exam, right? So mv divided by charge times magnetic field, right? Okay, now before, okay, we're getting closer to the end of the class, right? So now, before we go, let's now answer one question and derive the formula. Is this motion, is it a periodic motion? Of course it does, right? It is a periodic motion. So this particle is going to circle, right, as many times as you have time. Right? So now, of course, logical question, what is a period of this motion? Let me put a new bullet, right? So the period. What is period meaning of period, right? Period is just time. It's just time for a particle, in this case for a charged particle, to complete one oscillation, to complete this one circle. It's just time to travel over this distance, which is equal to circumference of this loop, right? And you know what, on the exams, so on the tests, quizzes, right? So I notice whenever I ask about the period of this motion, lots of students, I know 50–60% of students, they just panic because it's not a motion along a straight line, it's kind of circular motion, and they overcomplicate the situation. So the answer for this question is quite simple, and everyone who is in this class, right, behind the screen, knows the answer, but maybe you're not realizing this. What's the logic? Logic is very simple to answer this question. Look, let's start with a simple situation. Let's assume that we have a straight trajectory, straight line. Some bug travels along a straight line. And let's assume that this bug travels with the constant speed. Let me, one additional minute. With a constant speed. Let's assume that we know the distance. We know this constant speed. How can we find travel time? The question is banal. It's kind of insulting for students of your level, right? Of course, you just take the distance and divide it by the speed. That will be the travel time, right? Of course, everyone knows that. Now, what if I bend my trajectory slightly and still assume the same thing? I know the distance, and I know that the bug travels with the constant speed. Uniform motion, right? So still constant speed, like 5 meters per second. So what will be the travel time? Exactly the same. Take the total distance divided by the travel time. The key word, because it travels with a constant speed. And if I keep bending my ruler, and eventually let's assume I manage to bend into a circle. And the same. So let's assume that we know the distance, and we know that the bug travels with a constant speed. We have uniform motion, constant speed. What will be the travel time around one circle? The same, the total distance, which is 2 pi r, divided by the speed. And we do have uniform motion. The speed is constant. Here, from the tangential direction, we found that speed of this particle is constant. We have uniform motion. And then we added circular, so it's a uniform circular motion. So how can we find the travel time over one circle? Distance, which is circumference, 2 pi r, this, and divided by this speed. All right? So it's trivial. The question is trivial, but again, I noticed every semester, I know more than 50% student at this point, if I ask a question like this on the exam, they just write a bunch of rubbish. Although I know that everyone knows the answer, right? Okay, so in this case, T equals, it's just a 2 pi r cyclotron divided by the speed. Okay, so now let's plug our cyclotron radius and we'll call it a day. 2 pi over v in cyclotron radius and v divided by qb. You see what happens with velocity, speed, it gets cancelled. Speed basically is the magnitude of velocity. So it will be equal 2 pi times mass of the particle divided by charge times the magnetic field. And then, of course, you can easily also find the frequency. For example, it's a reciprocal of t. And what is important, period does not depend on the velocity of the particle. How come? So if particle, let's say, moves fast, if v is large, speed is large. Look, if speed is large, it's in the numerator. Radius, cyclotron radius is going to be large. So this circle is going to be large. So as a result, distance traveled by a particle is going to be larger. So speed is larger, distance is larger, and you have a travel time, let's say, 5 seconds. And then if you discuss particle with a smaller speed, smaller radius, circle is smaller, distance travel is smaller. So again, that time, so smaller distance with a smaller speed gives you still the same travel time, let's say 5 seconds. So every time they magically balance each other, right? So every time, if you have larger speed, you will have just larger circle and larger travel distance, but the travel time is going to be still the same. And mathematically, it's here because velocity gets cancelled. Right, so then, of course, we can, since we started talking about the period, so let's just also introduce the frequency, right? Which is the reciprocal of period. So frequency, of course, you can f cyclotron, it will be 1 over period of cyclotron radius. And of course, it will be just flipped that expression qb divided by 2 pi times mass of the particle. Right? Okay, so and now let's look at sort of a general situation. Let's assume that we have, I don't know, magnetic field lines pointing in a certain direction. And now let's send a particle neither parallel to the magnetic field lines nor perpendicular at some arbitrary angle and discuss what are we going to get in that case. Okay, so now let me put a new bullet, right? And now let me write, so general situation. General, oops. Probably I will draw it here. So let's assume that I'm just trying to estimate the amount of space I might need. Okay, let me draw. Yeah, here it's better. So let's assume that we have these magnetic field lines. So this is B. Uniform for simplicity, right? Of course, it doesn't have to be, but in order to discuss conceptually what will happen, it's good. And now let's send a particle. Probably I will send it which direction? Probably something like this. So let's say this is our velocity. So you see now it's neither parallel nor perpendicular to the magnetic field lines. So it's neither this nor that case. So what will be a trajectory? In order to understand what will happen in this case, we have to decompose this velocity in two components. First component will be parallel to the magnetic field lines, and the second perpendicular. And we know how, we just discussed, we know the trajectories which will be produced by those components, right? Okay, let me, along magnetic field line, so this will be, which way I label it? V parallel, right? You see, parallel component of the velocity along magnetic field lines, and perpendicular I'll probably draw it here. So V perpendicular component, right? Yeah, so we can write, so V equals V perpendicular plus V parallel. I can decompose any vector along any direction. So here, my chosen direction is the direction of the magnetic field lines, right? And then, of course, what? Parallel component is going to give us, it's this situation, uniform translational motion. So this component, this velocity is going to be exactly the same, stays the same, right? So a particle will travel along the magnetic field lines with this parallel component of with this velocity. And perpendicular component is going to give us a cyclotron motion. So it is going to, because of this component, a particle is going to circle around these magnetic field lines. And now, so if we superimpose these two motions, translational motion because of this component of the velocity, plus circular motion around magnetic field lines, what are we going to get? We're going to get something like this. So circular motion plus translational motion along the magnetic field lines, we're going to get helical motion. Helical motion, right? So if you superimpose this motion, uniform translational, with uniform circular motion, you're going to get helical motion, helical motion. Okay, so now let me draw this helical motion, to the best of my abilities. All right, so it will be something like this. All right. Helical motion, let me label it. So, all right, and of course here to describe this helical motion, you need to use two parameters. First, cyclotron radius, right? So you can introduce, so this will be R cyclotron, right? Cyclotron radius, and then the second parameter, which we haven't used up to this point, it's a distance between these, for example, 2 points. If I take this point on the trajectory and this point on the trajectory, right? This, what is called the pitch. Okay, let me show it. So P, and it's called pitch. Oops. Overlapping. Okay, the distance between these 2 points. Okay, so that's what I was planning to discuss about the cyclotron motion, right? And now let's start looking at example. All right, and example, I will probably, now I have that picture, I will probably move to this side. Okay. Yeah. Damage. Why I stopped? Because there will be another section, right? And I wanted to recycle these pictures again also. That's why I stopped. Maybe I'm thinking just using that whiteboard only, this part. Why not? So the problem is, what's the number? Where is it? 65. So it's 2965. Right. So what do we have in this problem? We have uniform magnetic field. Magnetic field lines, let's assume up, straight up. Right? Okay, let me draw them. So these are my magnetic field lines. Okay, I'm trying to draw them with the same density. Okay, then there will be a particle entering these magnetic field lines at a certain angle. Right? And we will have to describe that motion and find a few parameters. Right? But before I can write what we have to find, let me introduce coordinate system and draw a few lines on the picture. So let me introduce coordinate system, and the coordinate system, z-axis, I will point up along magnetic field lines. You remember, you can orient your coordinate system any way you want. So let's say this is z, then this is x, and, okay, nope, this will be y because I want to use right-handed coordinate system, so this is y, and this is x. Okay, so my coordinate system. Now, particle, and that is electron. So now, let's assume that we have an electron. Electron, E minus, enters this magnetic field at angle theta relative to the xy plane. So probably I will draw something like this. So this is velocity of that electron, and this angle theta is 30 degrees. Right. So electron enters the field, our magnetic field, at theta equals 30 degrees. So what else is given? Yeah, the magnetic field strength. So actually I didn't label that this is B. Right. So the value of B, let me check, 30 millitesla. Then velocity. Probably I wouldn't be able to write velocity over there. So what's the value of velocity? V equals 5 times 10 to the power of 6, right? Yeah, 6 meters per second. So that's what is given. What needs to be found? Let's wait for a few minutes, right? So first let's discuss trajectory, and then I will be able to write what needs to be found. So it's basically this situation. Velocity is neither parallel to the magnetic field lines nor perpendicular, right? But of course, this velocity we can decompose, right? Along magnetic field lines like here and perpendicular, right? So I can find, for example, this component. Let me label it as V sub z, because that is z direction, right? So I think I label it Vz, yeah. V sub z, and then component perpendicular, it will be this, right? So V sub y. So two components, so it will be V can be written as V sub z plus V sub y. Can we find those components? It should be a big deal, right? We should be able to find easily those components. So which one I wrote first? Okay, let's start with Vz. So magnitude of V sub z, it's just a V times what? Sine of the angle theta, because that side V sub z is opposite to the given angle. So it will be V times sine of theta, right? And of course you can calculate. So this is, which way I wrote, it's component parallel to, it's a component parallel to B. And which trajectory is going to give us? this component, it is going to give us a uniform translational motion. It was here in the corner, which I erased, right? So it's going to give us a uniform translational motion, right? So this gives a uniform translational motion, of course, along magnetic field lines, along B. Right? And then second component, V sub y. Of course, it will be V times cosine theta, right? Because it's adjacent to the given angle. So it's a component perpendicular to B, right? And this gives us circular motion, which we call the cyclotron motion, right, in this fancy term, but it does sound fancy, right? So it gives us a cyclotron motion. Let me move to another line. Gives us a cyclotron motion. Right. So we're, of course, a superposition of these two motions, we're going to get a trajectory similar to that one. Helical motion. Okay, so let me draw that helical motion. So it will be something like this. Right? And now we can write what needs to be found. First, we need to find cyclotron radius. Okay, so now what needs to be found? R cyclotron, because of this component perpendicular, we're going to have cyclotron motion. And the second, we will have to find this pitch. Right. So it's basically distance between these 2 points adjacent. Right. So this is P. So we need to find that P, which is pitch. Okay, so now the whole problem is here. And now we just need to find these 2 parameters. Let's start with cyclotron radius. I erased the formula on purpose. No, actually, no, not on purpose, right? I wanted to save it. All right, let's just quickly derive that formula. Yeah, because usually, as I told you, I don't give that formula on the formula sheet. Right? So let's start with cyclotron, R cyclotron, right? So it's just a application of Newton's second law in the radial direction. So component of the force in the radial direction equals mass times centripetal acceleration. So this is Q V. Okay, which V? When we derived the formula for cyclotron radius, right? So the whole velocity was perpendicular to the magnetic field lines. So back then, the whole velocity was perpendicular to the magnetic field lines. But now it's not only V sub y perpendicular to the magnetic field lines. So, of course, we have to use here V sub y. Right? Again, it's a very common place for mistakes because students just grab the velocity, whatever velocity is given, and use it in a formula for cyclotron radius. And, of course, that is wrong. Right? Because only perpendicular component gives us this circular motion. Parallel gives us a uniform translational motion, right? Okay, so V sub, okay, y, and maybe I will circle it to emphasize, right? So V sub y. And, yeah, magnetic field. Because the angle between them is 90 degrees, right? So QVB and sine of angle between them, and sine of 90 degrees. Okay, let me write it down. Sine of 90 degrees, right? And it equals to mass times centripetal acceleration. And again, velocity in the centripetal acceleration must be that perpendicular component. mv squared y over r cyclotron. Right. Okay, again, 1v gets cancelled, and we're getting the formula. You see, just basically one line. So from here, r cyclotron equals to mvy divided by this q b mvy q times b. Again, the major problem over here, right, so where students make mistakes, use the right velocities. In one part, you have to use v sub y, in the second part, v sub z, but here, v sub y. Okay, so that's the formula which I just erased, right? But now we can easily derive it. We easily derived it. And so now we plug numbers. Okay, I'm not going to plug numbers. I will just write down the answer. It will be 0.82 millimeters. So less than a millimeter. So the cyclotron radius, so it's going to circle with the radius, along a circle with the radius of less than a millimeter, 0.8 millimeters. Okay, so now, next step must be finding the pitch. And before we can do that, let's find another important parameter of the cyclotron motion, period. Let's find the period. Right? Again, you remember what is the period. It's just the travel time for a particle to complete one circle. Right? So that is done. So now let's find period t. And we discuss it. You remember, it's just the total distance traveled, which is circumference over one for one period, divided by the speed. Right, so it will be 2 pi r cyclotron divided, and again, which velocity, which speed do we have to use? Perpendicular component, v sub y. v sub y. Right. Okay. So r we found, y component you can easily calculate. It's a v cosine theta, right? And 2 pi r cyclotron, some mess, divided by v times cosine theta. So if you plug numbers, because everything is given, speed is given, angle is given, you will end up with 1.19 times 10 to the power minus 9 seconds. So nanoseconds. Slightly more than 1 nanosecond, 10 to the power of minus 9 nano. Right. Okay, and now the pitch. Right. And you know what, several years ago, I didn't discuss this problem in the class. I would assign it as a homework. And with the pitch, that's where most of the troubles students had. But actually, the solution is quite simple. So pitch, it's this distance between these 2 points. Do we know the speed in that direction? It's a v sub z, which gives us displacement of the particle in a z direction, this uniform translational motion. So v sub z is responsible. So we know the speed of the particle in that direction. Then, do we know the travel time between this point and that point? Do we know that travel time? Of course, we've just found it. It's a period. Because, okay, this is two motions like this translational, uniform translational motion and this cyclotron motion, they're coupled through time. So as a particle completes one circle in this cyclotron motion in this direction, And over exactly the same period of time, particle gets displaced by one pitch. We have helical motion, right? So we have one circle in this perpendicular direction, and the period is t, but also the same over the same period of time. Particle gets displaced from this point to the next point, covering that distance p, right, that pitch, in a z direction. So this period, which we just found, it's also a travel time for a particle to move from this point to that point, right? Because we have periodic motion, right? So, and this part, realizing that period, this travel time, is also actually the travel time from this point to that point in a z direction. That's where students struggle. And that's why I decided, okay, I have to discuss this problem in the recitation classes, because this part, tons of students couldn't realize. Okay, so now we can write, so P equals, again, V sub Z. It's another place for tons of mistakes using the proper velocities. We're talking about motion in the z direction along magnetic field lines. You have to use this velocity V sub Z. N times the period we just found, right? So period is there. Component, z component, v sine theta. So everything is given basically. Sine theta times t. So, and if you go through this, you will end up with 3 times 10 to the power of minus 3 meters. So which is 3 millimeters, right? Yeah, 3 millimeters. So the cyclotron radius is less than a millimeter, and over one period it gets displaced in a z direction by 3 millimeters.
I think your mic's muted.
Yeah, thanks. Whenever I drink water, I mute myself, and occasionally I forgot to unmute myself. Okay, so the next problem, conceptual. A couple of conceptual questions. Okay, I'll probably erase this. These questions I give among multiple choice questions quite often. So this is conceptual question 6, A and B. CQ6. Okay, it looks like I need to change blue marker, but all the time these blue markers, green markers, they're kind of bright, difficult to see them. Not enough contrast. Okay, so let's assume that we have magnetic field. It's a part A. So magnetic field lines into the board. Okay, so that's B. Then, which particle? Positive particle, for example, proton, enters these magnetic field lines. Okay, so let's assume that this is positively charged particle. Q enters magnetic field lines this way. Okay, perpendicular to the magnetic field lines, right? And so we need to answer the question, what is the direction of deflection? Right, so what is the direction of deflection? Direction of deflection. So in order to answer this question, we just need to what? Realize that the force, so we have charge, which travels, moves in the magnetic field. Of course, there must be magnetic force. We know the expression for the magnetic force. Q, V, cross, oi, what an ugly cross, V cross B, right? So let's apply it. So V cross, okay, conservation of brackets. If you open 3 brackets, you must close 3 brackets, right? If you open 2, you must close 2, right? Okay. Direction of the force in the first, again, 2 steps. You need to check direction of V cross B and then check the sign of the charge. V cross B, V that way, right? B is into the board, so I have to position my hand like this, so I can curl my fingers in the direction of the second vector in the product. And my thumb gives me direction of the cross product, and then second step. So direction of this is up, and since the charge is positive, so that direction gives us direction of the force acting on this particle, right? So force is this way. So force is this way, right? And as a result, we're going to have circular motion, right? A cyclotron motion, and the particle is going to circle this way. So I can draw a trajectory, so it will be moving that way, circling, if it have enough space, right, in order to circle. Otherwise, it will be, I don't know, quarter of a circle, maybe 1/8 part of the circle. It depends how big the magnetic field is. All right. So next. Next part B. Right, B. So now let's say magnetic field is given by dots. Right. So these are magnetic field lines B. And particle enters. Now let's assume it's an electron. Electron minus Q, and enters this field in this direction, V. So again, the same question. What is the direction of deflection? Again, so cross product, V cross B. V is up, magnetic field is out, right? So I have to position my hand like this. So along V, and then I can bend my fingers in the B direction. And my thumb gives me direction of V cross B. So direction is that. But that is only direction of V cross B. But since our charge is negative, right, it's an electron. So that direction must be flipped to this one. So the force will act on the electron that way, right? Don't forget about the sign of the charge. So in this case, force will be this way. And the particle is going to experience, again, cyclotron motion, is going to move along the circle. But now this way, it's this way. Again, cyclotron motion still, I can remind on this. So it's a cyclotron motion, both of these trajectories.